right, good afternoon, folks. First of all, thank you all for spending your precious time with us today and being so patient from the morning. So thank you. Before we begin, how about that passionate talk from Debendra, right? I'm inspired. Let's move all die-to-die interconnects to UCIe already, right? So I'm going to go through, what is it going to take to realize that vision? Okay, so, I need to move to the next slide. Okay, so my name is Nathan Kalyanasundaram. I am a corporate fellow at AMD. So this is the last session today. We're going to walk through software, manageability, and security. Okay, but when I said, what is it going to take? It's going to take a community. So that's what I'm here to say. All right. Debendra talked about the high-level goals. Because it's a long session, I'm going to repeat some of that stuff. What is the goal for UCIe? Chiplets are already here. It's proprietary. Lots of chiplet-based products are being deployed already. But there are significant challenges to bring forth the chiplet ecosystem, right? And I'll outline some of those. We'll walk through system-level topology examples. There's a number of them which Debendra had talked about, and then Swadesh had gone through some of them. But I'm going to just show some high-level examples and how we would set that up, and then go into a little bit more detail from the high level into what are the software registers, what's a DVSec, and then finally with some manageability and security overview. Right. So there's a lot of work to be done in the consortium. So I'll spend bulk of the time on the first part, which is the software section, and then maybe 10 minutes each on the manageability and security. Okay, so Debendra talked about Moore's law slowing down, and I think we all see that in all our products, right? So, how do we extend the legacy of the Moore's law? And one of the things which Debendra also spoke about is systems and packages, which will allow us to extend that legacy. Right. So, and the focus is going to be focused on ease of deployment and accelerate the ecosystem development. Right. And it's going to be extremely important to figure out a way to accelerate adoption of UCIe. And to that extent, a lot of things are being done the right way. Compatibility with existing software for fast adoption. So that's number one. It builds on the PCIe CXL software constructs, the DVSec, which is the extended capabilities registers, which PCIe has defined, and then the link can be managed by firmware, right? So for interoperability, we need to be able to bring up that link. It has to seamlessly come up and work the first time. So using existing facilities is going to help with that effort a lot. CXL and PCIe protocols, why is that important? And I'll go through that in the next slide as well. But those are existing use cases. So we have today accelerators which are existing on the system. So the first option is to bring them in onto the same system, package. And finally, reduce the complexity, right? So wherever possible, we want to reduce the complexity and not make it too complex. One of that example is dropping, if you're familiar with it, the root complex integrated endpoint, which was in CXL 1.1, there's no reason to support that currently. So on UCIe. All right, so this is a very high-level example of an SoC, right? So there's an anchor die, and it's labeled as an anchor die, and we'll go into what an anchor die is. But there's some amount of compute all around it, right? So there could be a memory controller PHY, there could be a CPU, there could be inference accelerators. Some of these the structural dummy, which you see is really related to process, but you may have to build it in some technologies, but not in every one of them. But at a high level, that's how it's going to look, right? So it's either a standard package or an advanced package, and we'll be able to integrate lots of components. So that's the ultimate goal. And ostensibly, we've called it Universal Chiplet Interconnect Express, labeled after sort of USB. But at some point, we want this interconnect to be proliferated like that, right? That is the goal. that we should be able to create a chiplet ecosystem which makes it really fast to build products, and especially not just the high-end server products, but even the edge products as well. Okay, so why PCIe and CXL, right? So the entire industry for the last 20 years or so has spent considerable amount of resources in developing PCIe-based technologies. CXL leveraged PCIe, so we started investing in CXL, and UCIe now leverages PCIe and CXL. So it's going to, first of all, as I said, accelerate adoption, right? So why is that? Why is that the case? The software is the same. It's extremely important. So the software, the device driver, the software model for for dispatching work queues, things like that are all exactly the same as if they are on the platform, right? So that's a big advantage. Address translation services, those are also exactly the same, right? So people are already starting to invest how to do ATS and ATC. CXL requires it. You cannot even do CXL.cache without supporting ATC and ATS. So that's another advantage because it's already existing. Error isolation and recovery, that is also being defined by CXL, by PCIe. And anyway, we can go on and on, right? So a lot of manageability, security, software, all of those features are existing, and every company wants to leverage that, right? So there's no reason to go invent again something new. Okay, so that's the first, and there are many examples of use cases, right? So there's inference accelerators already being deployed. There's crypto acceleration, compression, video codecs. There's just a bunch of things which are already being deployed today, right? And again, this goes back to extending the legacy of Moore's law through domain-specific acceleration. So if we can bring that all into the same socket, same system in a package, that's going to be a big advantage to all the products being developed in the future. The second use case is SerDes, right? So SerDes are getting significantly more complex. So already PCIe, the industry is struggling. We went from 32 to 64, now to 128. The next generation will be 128. Gen 7 has already started. Ethernet has gone from 50, 100, 200, 200 gig, and next will be 400 gig. And these are all driven by HPC, ML use cases. Right, so they are becoming more and more specialized, and not every company wants to. Already IPs are being bought and integrated, right? So the next step is to build chiplets, and which can be directly deployed into your system in a package. Co-packaged optics is another specialized product segment, which is also going to need some form of standardized connectivity, and we'll look at it on the back end. UCIe is not going to define any of that. UCIe is not going to define cabling, what sort of optical technology we're going to use. However, we need to be able to enable to run some protocol for the use cases that Andre already outlined. The next use case is memory, controllers and PHY, right? So there's plenty of memory technologies. New memory technologies continue to pop up. We have HBM, LPDDR, DDR. There's just a variety of technologies which are being developed, right? And if there was a memory controller available, not every company has to build them, and they could be integrated and used. Now, maybe not in the highest end, but again, this goes back to if there are lots of edge products coming out. If you want industry to drive the innovation of bringing out new products at an extremely low cost, it's going to be important that we start to define these use cases. So UCIe is going to look at how to enable memory chiplets, and that's already in progress. We're expecting something to come out in UCIe 2.0. Right now on UCIe 1.0 and 1.1, it has to be some sort of a raw mode. The last one is sort of generic compute attach. So what I mean by that, can you replace an x86 with an ARM or a RISC-V? Is it easily replaceable? Now, that's the holy grail, which lots of people want to do, but there's a long way to go. And I want to say UCIe is not looking at that, okay? Because we get asked, is there a way to do multi-ISA? But those are, longer term issues, and I would say it's not that simple to do that. All right. So now these are the challenges, right? Okay, so we have a vision. We want to execute on that vision. And I think everybody has agreed that the industry is going to go in that direction. However, as I said, it's easy to do proprietary things. But to create an ecosystem is a lot more challenging. So let's look at some of those, right? So the first is protocol, electrical, physical. Every consortium is going to define that well. I mean, that's bread and butter. You have to define it first. And UCIe has done an extremely fine job in defining that, and that's critical for anything, right? However, the rest of the chip functions also has to be done, because in order to create an ecosystem, if you don't do that, it's going to delay the deployment. Right now, it's possible that there are partner companies who join together and develop some initial solutions, and then later on the true ecosystem forms. But it's important to think about how are we going to enable this chiplet ecosystem, right? And that's where software comes into play. All right, so the security and manageability, debug and test, power, thermal, RAS, right? So power issues are also a big problem, right? Like, for example, when PCIe defined it, PCIe defined footprint. They defined the add-in card specification, M.2, M.4. UCIe needs to have to define that as well, right? What is your chiplet dimension? What is the cavity in which you're going to fit it in? What is the power level of that? So there's a lot of effort still ongoing, and those are harder problem to resolve. It will happen over time. It's not, we're just highlighting that those are also need to be resolved, right? And power delivery. So there's a bunch of stuff. There is also challenges in the business processes. So what is that? Logistics, right? Where is the chiplet getting manufactured? Who's manufacturing it? Is that an OSAT you're sending it to? Mixing foundries, right? Those are all important issues. It's not that we are going to, as technical people, going to solve, but industry has to come together in order to enable that. But as people build products, we're expecting that all of those will come. The final thing is system test. Who is going to own the system test? How are you going to deliver that content, right? Is every chiplet manufacturer going to provide a content which gets loaded and tested for the system level test? Is it the onus is on the system integrator? Lots of issues like that need to be resolved. And, again, I want to stress that it will get resolved, but those are things which we are thinking about and how to resolve them. Okay, so the next is a chiplet ecosystem solution stack, right? What does it need? What do we need to create this ecosystem again, right? So if you look at, say, UCIe, there is two independent hardware stack, right? And I think a lot of things we discussed before. One is the main band, which is the protocol. So the protocol could be CXL, PCIe, some sort of a raw or a streaming protocol like CHI, AXI, could be even a proprietary protocol, which is proprietary to Intel or AMD. All of those are going to be using the main band, right? And then there's a control, which is a sideband. Regardless of what the main band protocol is, the control needs to be the same, right? We want most of those functions to look and feel the same. And the focus of the software stack is that, right? So certainly for the main band, how you dispatch work, there are device drivers, all of those models already exist. However, for the control is where we want to start to define those. No, I don't want you to take this as a literal stack of software thing, but it's really more like services which we have to support, right? Services which we'll have to develop over time to run all of those things. So the first and most important thing is the die management unit, right? There needs to be some form of a die management unit in order to run all of these services. So the first is, for example, secure boot, reset, and repair. There's chiplet firmware authentication, runtime firmware operation, manageability, which is, again, we're going to think of using SPDM and MCTP. That's already being defined. There's runtime RAS, security. There's lots of these services which needs to be standardized in order for us to create a true chiplet ecosystem. On the top, we have the scalable design verification, right? So we need the CAD houses to be able to run, to be able to emulate this platform, right? It's going to be extremely critical, more so than before, to at least co-simulate in some way before the chip gets manufactured, right? Because otherwise mistakes can be very expensive in this. So we need a significant effort, from all the companies like Synopsys and Cadence to support many of this. And then there's the production testing, which I already talked about, right? Who's going to build the content? So all of this, I have to say, it's being worked on, and it's going to take some time. But as products start to show up, you're going to see that all of these are going to get built. Okay, so any questions? Let me pause there for just a minute, since I sort of went through that a little bit fast.
Yeah, if you go back to the previous page, UCIe leveraging CXL is brilliant. But there are also some fundamental differences. And like when you look in here at SPDM and MCTP, with a module, a CXL module, fundamentally, each module is going to have to own that.
Yep.
So you're going to have that logic duplicated, and we're talking about a fairly significant section of logic, maybe 600,000 gates of logic, 16 kilobytes of ROM for the signatures, and it just is one of those things that you have to absorb into the cost of the module. Chiplets could potentially be a different thing, because if we look down the road, where we would love to be is that you go to DigiKey or you go to Mouser and you order a die and drop it into your chiplet and literally have that mix and match solution set like we have had for printed circuit boards for the last 50 years. If that is indeed the end goal, consolidation of those kinds of functionalities versus this disparity of a wide variety of suppliers, how do you connect those dots? How do you see cracking that nut where you get an industry to act like a consolidator in some of these requirements?
I don't have an answer for that, right? So that's why I'm listing these as challenges, okay. Right? We as a community have to solve them, because it is a hard problem. Okay. However, bringing them out as challenges which need to be resolved at this stage is going to help us get there a little bit faster, right? And when we get to the manageability section, you'll see that we've set ourselves some guardrails to the point you were talking about, right? If every link has to have 60,000 gates and 64 kilobyte RAM, that's just not going to be a scalable solution. So we certainly have to come up with and that's why it's going to be important, right? I mean, like even in this one, how do we do production testing? Scalable verification platform to do emulation. So these are all, initial phases, right? Because it's going to take some time for us to, start to be comfortable in this space, right? There is no product which exists today. People are extremely comfortable at chiplets. No question about that, right?
Yeah. It's great to hear you express it as an outstanding question. Yeah. I'm driving this for JEDEC. And in JEDEC, we're tackling this by a proxy system by which we can consolidate that logic into one place and have that logic proxy for the entire assembly. And it sounds like you guys are going to need to face the same challenge. This is an area where we can communicate.
Absolutely, and I think we already are going to do a MOU with JEDEC on a number of things. So. Yeah, I mean, we don't need to invent everything in UCIe, and we won't. Industry.
And worse, we don't want to go in two different directions.
Absolutely not.
Right.
Yeah. I don't know if you want to add anything more, Dibendra.
No, I think you said it really well. And again, right, I mean, a lot of the things that we are looking at, we are looking into, MCTP has done certain things. We want to leverage those. So as you will see, right, that's the theme. Only do things that are absolutely essential and then leverage. And I think your thing is spot on, right? Just do that functionality in one place and everybody else just uses it as a proxy. Right?
All right, so we're going to get into a little bit more detail on some of the use cases which we already talked about, right? So let's start with the simplest use case on the left-hand side of your screen, right? So that's the, some sort of a, host interface, PCIe, CXL, or potentially, some proprietary streaming protocol, right? It could be driving chai, it could be driving some internal Infinity Fabric protocol or something like that. And what does it take, right? So there is the already Swadesh talked about, this is a single link, there's a die-to-die adapter, there's a UCIe PHY. Even if you're running the proprietary protocol, the request from the consortium is to try and use the same set of registers, right? Or at least model them after the DBSec, which are being defined. Because if everybody goes in completely independent direction for each one of those links, it's going to create some form of a confusion. It's not like it cannot be handled, but where possible, if we can use the same set of registers in register format, which are being defined for a link, it's going to be extremely. I mean, it'll help with interoperability, right? Because you have to be able to bring the link up, monitor the health of the link, number of things, and monitor activity, performance monitoring. All of those becomes easier if there's a standard way for all links to operate. Okay, so the middle one is another example which Swadesh talked about, is running multiple protocol stacks on UCIe, right? So what is the use case for that? Let's say you take a device, and the device is a PCIe device. You want to be able to do PCIe services like address translation services, right? Those are going to be that's because that's a standard way of doing it. However, the main band doesn't have to be CXL. That could be something else. As we said, we're already provisioning for the sideband to have a certain set of services, and that's a controlled services. And then we have two sets of protocol. There's the PCIe, CXL, and you could use one for the address translation. Just like think of another easier example. Think about is CXL.cache versus CXL.io, right? Those are two independent protocol. Although those are both defined in UCIe, but you can replace that CXL.cache with something else. Let's call it AXI. So and it allows, so there's an enhancement which has gone into UCIe 1.1, which allows us to run multiple protocol stack on the same set of PHYs, right? So, and that's there's already people who have asked for it, and it's an extremely useful feature to have. The third one on the thing is a PCIe, switched PCIe CXL, right, over UCIe. So you can have a, die 0 could be, let's say, a host processor, and then there's a die 1, which is a switch, and then you can have a multiple switch downstream port, and then you can also go out onto the link. So all of these are possible, right? That doesn't mean that this is how it's going to be, but this is a little bit more of a complex example. You'll see that there's multiple chiplets tied in a series, and you can run the, ultimately go to a CXL link directly off of this setup. Okay, and then the left one is the example of optical link, which which I already described, right? And Devendra, talked about that. The protocol which we are going to run, and the reason people are moving to optical is that when you get to these 200 gig and extremely high bandwidth, high bandwidth at low power is going to be critical, right? So power is becoming a big issue. So if once we move to optical, what is the protocol we want to use? I mean, now it can be any protocol. However, we have for memory disaggregation use case, which is what is described there. we can use UCIe optical directly, right? So the memory could be on a different, completely independent, entity in the rack, and you can directly go from the CPU socket to the to the disaggregated memory. So that's the use case which we are going after, at least for this. So and the interface which is going to be used directly there could be CXL protocol, it could be something else, but ultimately from the end-to-end perspective, in this case it's a CXL, but it could be a streaming protocol as well. And you'll see that on the other side we have DRAM associated with it. There's a die which provides a communication channel from between optical links. Okay, and then the last one is the SerDes solution, which we talked about also as an example. And this could be pipe interface, right? It doesn't have to be CXL or PCIe. It could simply be the pipe interface, which we just expose that as a streaming interface to the UCIe PHY, and then it'll just go to the at least you'll get the proprietary SerDes solution. So this is just a high-level view of the software, right? So what do we need to do in order for us to interoperate, right? So it's going to be the first and foremost, how do you enumerate? How do you discover a link? How do you bring up a link? How do you do enumeration? All of that needs to be standardized, just like a PCIe would. So UCIe has modeled itself after PCIe, right? And PCIe is something which has been around. People understand it very well, as I already stated. So the first thing is the UCIe link has to be discoverable by the OS. So there's this new structure being defined, which is the early discovery table, and that's going to be populated by the firmware, right? So that's really going to provide, and what you see on the left-hand side is there's two UCIe link. Let's think of that as coming out of the host. And each one of them has a base address, right, where it starts. So it's just an MMIO map. And firmware will populate for the OS to come and discover these links, what sort of a link it is, and the link properties. Those are, and so there's an ACPI table which is going to be created by the firmware to do that. The endpoint and the switch, that also needs to be enumerated, right? That's going to be enumerated by the DVSec, and it's going to be the device 0, function 0, and those are going to be configuration accesses to set that up. So so mostly just following the existing standard PCIe CXL software model for UCIe in order to do the enumeration discovery. And we'll go into the detail. I mean, it's apologies for these are all in the spec, but it's kind of really small. But once we there's also another picture coming up where you can see it in more detail. Okay, so there's the first thing in the extended capabilities register is UCIe Consortium ID, right? So there's a new vendor ID, PCIe defined vendor ID, which has to be populated in the DVSec. Now there's also discussion about should we use the existing PCIe vendor ID. So for anything which is PCIe compatible, it's going to be the vendor ID defined by the PCIe consortium. And if there are specific use case without PCIe, then there's going to be a UCIe specific vendor ID, which is also going to be allocated. And if you look at the list of things, right? So there's the extended capabilities header, there's a designated vendor specific header, and then we start with the UCIe link capabilities. So there's the control register, status register, which is all going to provide what the link width is, what stack support is. Like for example, we talked about the multi-stack. What is the packaging type, retrain, lots of information about that link and the capabilities of the link is going to be provided. There's error link and notification control status register. That's also standardized. So if there was an error, somebody can go query it, and we want that to be, just like any other consortium, to be standard as well. There are register locators for registers beyond the basic functionality of the DVSec, right? These are for test compliance, implementation specific, die-to-die PHY, and we'll go into the detail of what are the implementation specific ones for the die-to-die and the PHY registers. The most critical one is the mailbox, right? So we talked about all of these services, software services which need to happen, and all of that communication is going to happen through mailbox, right? So the command being delivered, the firmware being delivered. So mailbox is the main mechanism through which all of that communication needs to happen. So then there's the, again, for enumeration, there's independent, interdependent root port and downstream links for a multi-stack UCIe scenario. So, and once all of these registers are defined, and we expect that every link is expected to support them, it'll just be in a standard way it can be discovered. Okay. Again, my apologies. You can't see it very well, but all of these are available in the spec. So, so we talked about what the host side is, right? So the host side is going to have an MMIO bar, which can, we just access it through just regular memory loads and stores. For the downstream ports, there's going to be PCI config based accesses. So there's function headers which you can access through PCI config. If you notice that on the left hand side there is the capabilities block, and then the register block. We provided the next pointer to those blocks, and we'll get into the detail of what those register blocks are. There's a little bit more clearer view of it. Okay. So there are two kinds of register blocks, right? So there's the host register block, which is called as UCIe register block, and then there's a switch register block. It's just called UISRB, right? So that's, again, provides the base address for enumerating the UCIe links below the switch downstream ports. And it has to be included in the switch upstream config space. So we talked about how the UCIe, the host does it, right? So the host has a MMIO register space. And then we have a config space and a table header, which is in the device upstream port. And then that upstream port is going to have an MMIO bar and then provides a base address for the switch downstream port. So and it's, again, those are all going to look very similar how you go from a host to a switch to a device. So now hopefully you can see the screen. So the first thing is it has a capable. So how do you address that bottom, right? So there's a base address register, which is the MMIO base, and that provides the pointer to the next capability block. There's also a register locator, which is going to provide where each of those capabilities block and the implementation specific registers reside, right? So there's a MSI capability register. There's a UCIe PHY and die-to-die register. There's a UCIe compliance and test. So these are all register blocks, chunks of blocks, right? So you should be able to, go from one pointer to another. The one thing to note here is that there is a UCIe, so there's a PHY and a die-to-die, which is combined in the standard space. And then there's an extended space where implementation specific details are being provided. Now there's a specific ask when people buy IPs, right? You could buy IP, like a PHY IP from one vendor, the die-to-die adapter IP from another vendor. How do we detect, which one of them is what? And so you have to be able to decipher which IP is being used on a certain product. So that's why those have been defined. So those are implementation specific IDs. You can have additional vendor ID, additional information about the IP block itself, which is being used in all of these paths. Okay. The whole point of this slide is that the UCIe 1.1 has a integrated, the root port integrated endpoint, right? So that is being deprecated. We're not going to use it on UCIe. So the illegal columns are basically just stating that, right? So that's the whole point of this table. And it's important that people don't assume automatically that that feature from UCIe 1.1 is going to be supported. UCIe does not support it. Okay. So this is just a software thing. So we talked about it. So just to summarize what we talked about, right? So there's the PCIe CXL device integration model that is extremely well established. We want to first enable that so that the ecosystem can develop. We can, weather out all the kinks, instead of trying to, bring up something entirely new. It is going to help kickstart the ecosystem. It's flexible, extensible. Lots of different topologies can be built. And a lot of the examples you already saw, right? It can be a tree topology. It can be star topology. It can have all kinds of IP integrated, chiplets integrated. So all of that is feasible with the existing UCIe, right? And it's a mix of standard protocols and streaming protocols. The software model, as we discussed, is leveraged from widely adopted PCIe. And of course, it's backward compatible and scalable for future use cases. All right, I'm going to pause here for just a minute to see if folks have, and then we'll jump into the manageability section. Yeah, from my perspective, the biggest driver, well, there's disaggregation of memory, right? But the bigger driver is going to be for machine learning use cases. Now, one of the things is that CXL is currently tied to PCIe, right, data rates, and that is completely insufficient. So it's going to be critical for us to be able to jump that, right? You're still running CXL protocol with this global fabric attached memory, global integrated memory, fabric use cases. But in order to jump ahead, that's going to be the primary use case from my perspective, which is going to drive optical cabling, right? Because it's already being done. Oh, UCIe is just the transport medium in that case, right? And UCIe does support PCIe and CXL protocol. Yeah. That to me is the biggest use case. That's just from my perspective. But it can also enable new use cases once it has to get cheap enough, right? Until then, the machine learning it's an expensive proposition. So I think it'll come there first. All right, so let's talk about manageability, right? I would start at a high level. What is that we're trying to do, right? So the first goal is make a reliable system, right? So the improving reliability to reduce cost, right? That reduces replacement cost is going to be the first and primary goal. Availability, so monitoring the health of the system, taking preventive actions, that's going to be important. And then finally, serviceability, right? On an error, how do we gracefully shut down the system and recover from that failure and come back up again? So just the general RAS capabilities, the manageability software needs to be able to provide those services. And then from we already talked about, right, what else it has to do. So the manageability software needs to be able to do inventory management. So it has to go figure out all the link types, all the chiplet types, what are the protocols is running on it. So it has to first do an inventory of all the entire system on a package. It has to be able to configure those devices and control those devices. Right, and then the continuous monitoring the health of the system, whether it's thermal, power, and taking remedial action, logging errors, logging events, and then in the case of failures, it also has to be able to alert either the upper level software or the user, right? And then finally, just the ease of debug. That's all going to be critical because so far it's a lot easier in the system, right? But we are hoping that it will extend to the chiplets as long as it stays in this device model, at least for those initial use cases, right? But once you start to add memory use cases and other use cases, how do we debug those issues? So the manageability software and having a common framework for manageability is going to be extremely important. All right, so we, again, talked about, right, so there's a big list of services we have to provide through the manageability stack. However, we don't, focus on simple and efficient mechanisms, right? It cannot be too onerous that, it just falls flat on itself. And the manageability features which we are adding should support an open chiplet ecosystem, right? It cannot be just, a pinpoint solution, but it has to be extensible to a wide variety of use cases. So we won't pick something, either the SPDM or MCTT type, which is existing, and it already has a wide variety of use cases, right? So that's going to be an important thing. We don't want any complex protocols, right, which requires like a powerful processor on the chiplet. If the control processor there is going to be bigger than the chiplet functions provided, that's not going to be very useful either. So we want it to be lightweight. And then the footprint, both the hardware and the software, needs to be extremely small. To your point, right? I mean, it cannot be like this massive hardware which gets tacked on to every link. That's not going to be very fruitful. Okay, and then I already said this: the main band protocol. So the manageability has to be independent of the main band protocol, regardless of what protocol is run on the main band. The sideband services has to be able to work across all of them. We also have to enable the firmware loading, right? So these are the guardrails under which the manageability working group is working under, and as we start to define more and more services, we'll start to operate within these guidelines. Okay, so this is just another quick overview of the manageability hierarchy, right? So how do you even manage? So you have to establish an anchor. So there's some die, let's call it an anchor die. That anchor die has the primary root of trust, and it has the BMC communications, right? So it's going to communicate with the system, and that's where all your security protocols, everything gets established. It then extends the management hierarchy through all branches of this, right? And this is where it could be a tree, could be a star, but everything originates from that anchor. And in some of these examples, you got a compute chiplet, you got a connectivity chiplet. The connectivity chiplet could be just a switch, but you have to extend that manageable hierarchy through these switches. And we'll see when you get to the security section, these all creates, interesting, dynamic. Okay, so this is again I think I'll kind of, in the interest of time, go through a little bit faster. These are all the services again, right? So there's initialization, enumeration, firmware delivery, messaging, and events, right? Broadly, the manageability layer has to be able to do all of these, provide all of these services. All right. I think we got enough time. But you guys have been very patient, so don't want to take too much of your time. Okay, let's jump to security, right? So this is the last section. It's going to be, so as we add more of these chiplets, right, we also have sideband. All of these becomes an attack vector. So we have to think through, and there's lots of proposal in the industry, right? So there's, the threats could be counterfeit and compromised chiplets. People can do boot modifications. Not that these don't exist, right? All of these problems exist today as well. But because we have a sideband, that opens up a new threat model, right? Because that didn't exist before. So there's some new things which we'll have to think about and take care of. There's data leak, probing on the bus, and we have an example, how you could, probe the bus and why it's easier to probe the bus now. Accessing the debug port, because you have so much function and focus on debuggability. That debuggability usually also creates security holes, so we have to be cognizant of that as well. There could be supply chain issues, hardware, software. So security is going to be extremely critical in the system, and we have to think through all of the security issues pretty fast here. All right, so why is this new, right? So the die, the die is still not exposed, right? So once you remove the lid, you can, but the interconnect is exposed now. The interconnect was exposed previously as well, even in proprietary product is exposed. However, now what's different is that we know the protocol, we know the bump locations, we know how it is laid out, right? And know what the bridge chip is going to look like. So with that knowledge, it's significantly easier to do, the EMFI type, attack vectors, excuse me, to steal or to do invasive or non-invasive attacks, right? So those are possible only because we have standardized the bump locations and things like so. We have to now guard against that. Okay, so how do we guard against it, right? So these are all known. There's lots of known techniques which are being deployed in lots of other places, right? Like PCIe is deploying them. There's Link IDE, CXL is deploying them. There's TDISP for attestation. There's just lots and lots of features which are being added because there's a high focus on security across the industry. So we just simply want to leverage all the work which has been done, right? And only augment things which are absolutely critical or something which is completely new for UCIe. Okay, so the first thing the anchor die must do is the SoC root of trust, which is there. It needs to be responsible for the secure boot as well as chiplet measurement and attestation. Now, there's a lots of proposal for chiplet measurement. It's really measuring the delay through the network. There's a PUF proposal, which is physical unmodifiable function. So there's lots of proposal. We don't know whether we need to go that far, but there's simple techniques which could be used for measurement and attestation. Attestation is already being done, so that's going to be critical, right, for security. We don't want any plain text to go across this link, as we said, because the interconnect is exposed. It is going to be critical that all of that data which goes between the die to die is also encrypted. Yes, there's a additional power, but we have to. That's where we'll have to look at what is the cost of it. How do we do that? What else can we do? So there's something which which we're starting to think about, right? But security is a huge topic with opinions from like every company, every person. So it's going to be difficult to come up with a unified solution, but we're working on it, and then we expect that there'll be something. Okay, and then the anchor drive certainly has a root of trust, but you also have to have some form of a root of trust on the chiplet as well, right? Like for example, today the switch is not in part of the root of trust domain. Like we do an end-to-end encryption between the host and the device. PCIe does it, like call it Stream IDE. But here, I think it's going to be important that we bring all the chiplets into the root of trust, right? But if you're not bringing it, you have to be very aware that it has not been brought into the root of trust. Maybe it's an endpoint like a memory. There's some alternate mechanism by which it can be done. But at least for the majority of the chiplets, we are expecting that there's some form of a local root of trust. Okay, and then again, all the security policies are being established by the root of trust, and then it gets propagated to all of the chiplets in the system. Okay, that's my last slide. I think in summary, UCIe is an open industry consortium, and Devendra talked about this already. I think we have more than 120 members. We have released UCIe 1.0 specification, which is already available. UCIe 1.1 is imminent. We expect sometime this month. And then, of course, we want people to join and contribute. As I said, it's going to take an entire community to increase adoption and accelerate adoption. So it's going to be critical for people to contribute to our technical working group. So we have electrical, protocol, form factor, compliance, manageability, security, and software. The new working groups we added is automotive, which got added recently. And as I talked about, memory working group is something we're thinking about. I think the journey has just begun. I mean, this is the way of the future. It's going to happen. We need everybody's help in making it happen. Thank you very much.
Just because I know you don't have enough work to do. Now, this fairly short list of stuff you'll probably be done by the end of the day tomorrow. Yeah. One of the things we found in our work in JEDIC was that we needed to bring power sequencing in as part of the anchor function. And I suspect you guys may end up having to do the same thing, where what we do is during the power sequencing, we have a series of LDOs that come up, bring up the system management bus so that we can be doing that authentication, be doing that configuration. And amongst the tasks that thing takes on is finding out what voltages are going to be needed and at what currents, and then going out and programming the voltage regulation for the configuration that's been installed.
No, I mean, I think we definitely want to leverage many of those mechanisms, right? Anyway, we should talk, and yeah, I'm looking forward to it. All right, thank you. I think that concludes, and I think there's some kind of reception, I think, after this. So hopefully we'll see you all there.